Okay, so this is week 6, Tuesday. Agenda will be longitudinal shear on the beam section. Quiz 03 or the third quiz will be posted on June 10 and will be from homework 5. Okay. So let's look at today's topic on longitudinal shear on a beam section. Okay. So I'm going to take some of the images or figures that I've used or I posted on Avenue to Learn. So you can get all this on Avenue to Learn, okay, all these images. So when do, undo. So when do we apply longitudinal shear on a beam section? Okay, so when do we apply this is when we are going to analyze the strength of joints. Okay, I highlight here joints in shear loading conditions. So if you look at the figure below, or if you look at the figure below, what you can see is if I draw transformation, this is our X, Y, and this is our rotation in our Z. And what you see on the left hand side, this is the cross-sectional view where this is our Y and this is our Z and this is rotation of our X. Okay, so this is our cross-sectional view. And if you look at the cross-sectional view, right, this part is made up of 4 members. Okay, so you have member number 1, member number 2, we have member number 3, and you have member number 4. Right, so it's made of 4 parts, and where failure will occur, this failure will occur in this at the joints. Okay. So this is where failure will occur. Okay, so failure will occur at the joints. It's like human, right? Where we tend to fail is also our joints, our elbow, our hips, our knees. Okay, so it's the same thing. Is where failure will occur at the joints. Okay, so if we look at last week, okay, or the previous week, if we have a section, yeah, I'll try to emphasize on a figure that I can get. Hold on. Okay, like a diagram like this. Okay. Oops, beg your pardon. Like a diagram like this, or cross section. Oops, a cross section that look like this. Okay, I will zoom in. Don't worry. All right. So if we have a cross section, this is made of one solid piece. Okay, this is made of one solid piece. Okay, and we will know that failure will always occur at the centroid. For this case, not every case, for this case, the failure will occur at the centroid, right? This is because tau max is at the centroid. Now, if you look at the structure that we have today, right, there's no dispute, okay, there's no dispute that tau max will also occur at the centroid. Okay, so there's no dispute that tau max will also occur at the centroid. So this is where our centroid is, and at the centroid is where tau max will occur. Okay. However, failure will occur at the joints first because the joints are weak. Okay. So I will go into an example to highlight why that's the case. But before we go, we do that, we're going to calculate. Okay, the objective of this topic is we're going to calculate the shearing stress acting on the joint. Okay. So there are two things I want you all to remember. Okay. Number one, these are important. The member, okay, the member, which is what we call M1, M2, M3 before, okay, is to distribute the shear stress. Okay. So if there's anything to remember today, it is these two main points. Okay. The joints is to transmit the shear stress from one member to the other. Okay. And there's a new form, not there's a new formula, okay, that we're going to learn, and this new formula is built up from shear flow. Okay, so we know that shear flow right is the formula, if we were to recall, is Q, small q is equal to VQ over I. Okay, that is our shear flow. And if you look in terms of units, we look in our units. This is Newton meter cube over meter 4. Okay, so you cancel is Newton per meter. Okay, now there is another equivalent, okay, where we can determine the shear flow is also equal to the force that the joints or fastener could resist divided by the spacing of the fastener. And the units over here, so it's force, Newton, right? So if we look at the units again, it's again Newton per meter. Okay, so for this analysis, okay, we require for this topic, the most important thing we have to do is you require application on failure analysis. Okay, so we're going to do this. I'm going to work on an example. Okay, and we're going to apply what we learn over here or what we know over here. So the key things are these. Okay, the key things are the members is to distribute the shear stress. The joint is to transmit the shear stress from one member to the other. Okay, and this formula over here, the force that the joints of fastener could resist, divided by the spacing of the fastener. Okay, so now let's look at example number 1. Any questions so far from any of you? Okay, I don't hear anything. So let's look at example number 1. Today, I hope to do 4 examples on this topic, okay? I want you all to be very familiar with what is going on. Okay. So a double wedge girdle is constructed from 2 plywood sheets that are secured to the wood member at its top and bottom. Okay. So what we have over here is 4 members, right? A double web. So this is a web. Okay. So this is our web, and this is our web. Okay. So a secure wood member at its top. So these are your top and bottom member. Okay, so these are all your members. So the allowable bending stress for the wood. Okay, so the stress allowable for the wood, okay, is equal to 8 times 10 to the power 3 psi. Okay, so it's given. And the allowable shear stress, so shear allowable is equal to 3 times 10 to the power 3 psi. Okay. If the fastener are spaced 6 inches, so the fastener, as you can see over here, so if we look at a cross-sectional view, the spacing is 6 inch. And then each fastener can support 600 pounds. Okay. And I want to highlight what you see over here in a single shear configuration. So the resistance force is 600 pounds under single shear configuration. Okay. Okay, so now we are going to understand what all these numbers, why is the 8 times 10 to the power 3 psi is used for, what is the shear allowable used for, and why we are given the spacing and the resistance force. Okay, so what we're trying to do down here is determine what is the maximum P that we can apply. Okay, so in terms of transformation,